Okay, so I guess I can now say that we missed that part about the precision projector alignment tool. Okay. Have to get that one out of the way. All right. So first thing first, we go to topic 7. In topic 7, at the bottom part here is sample exam 2 questions. So we'll go through those, sample questions. There are really quite a bunch of questions, but I do want to go through every single one of those and kind of explain how to answer those questions. And also give you an idea of the scope of this particular exam. It is really kind of larger. The extent is more than what I expected originally. And that had to do with the first exam did not cover quite as much material as I first intended. Okay, so the first question, kind of has the form of this. Let me kind of zoom in a little bit more so we can all see better what kind of question we'll be getting. Okay, so I want you to give me a range of number so that the instruction add B, add byte, $78 to AL will make certain flags turn on and turn off. So I'm just picking a few here, CZ, O for overflow, and then S for sign. So we want to find out, okay, what values can you specify in AL that can make the carry flag turn on as a result of the add byte instruction. Okay, is the question itself clear at this point? Okay, so what is the range of numbers that you think will make the add instruction turn on the carry flag? How do we figure that out? Okay, so the first question is that we have to ask is, okay, let's focus on one single flag, which is the carry flag here. Okay, we know that AL can only have a range of values from 0, 0, 0, 0, 0, 0, 0, 0 in binary to 1, 1, 1, 1, 1, 1, 1, 1 in binary. So the question is, how do we make the carry flag turn on like that? Okay, first thing first, 78 in base 2 is what? Okay, this is 64 plus what? 64, it has no 32 after that, has no 16 after that. So the next one is an 8 and what? A 4, and there's a 2. Yep, okay, there we go. So knowing that these are the, okay, let me just write it down here too. So I'm gonna have this all captured as well. Oh, not the calculator. Mouse pad. There we go. All right, so we'll go ahead and express 78 as 64 plus 8 plus 4 plus 2. So that will make it a binary number of what? 64 is 1 followed by how many zeros after that? 64 is 2 to the power of 6, and as a result, as a binary number, it is 1 followed by how many zeros? 6 zeros, exactly. So we have 1, 2, 3, 4, 5, 6 to represent 64. What about 8? 8 is 2 to the power of 3, so we have 1, 0, 0, 0. 4 is 1, 0, 0, and then 2 is 1, 0. So we have to combine all of these digits in base 2, so it becomes 1, 0, 0, 1, 1, 1, 0. Is that okay so far? Okay. I can do this without a calculator. Okay. If you need a calculator, I can give you all the binary numbers to begin with, so this way you don't have to do any base conversion. But what is this going to do? I mean, why is this going to help me? Okay, because what we want to do is to figure out, okay, this is the first number. Addition is commutative. So we only have to figure out what pattern do we have to specify here to basically trigger a carry flag of 0 and then a 1 over here. That's the question, okay? How can we make the carry flag a 1 when we know one of the numbers is this one here? Sorry? Okay. Well, there are several ways to look at this. The first way to look at this is to say, well, specifically, how do I turn all of those into zeros so that I have one carry flag being on and then all the other digits being 0? Yep, do a subtraction, right? So in order to do this, to figure out what these question marks are supposed to be, in order to make this happen, what we can do is to say, well, what is this thing minus this thing here? Well, let's do the subtraction. So we have a 0 here. I'll do it the same way that I usually do. Have one row for just the borrows. Okay. All right, so now we can switch to here. 0 minus 1 is 1 with a borrow, and then 1 minus 0 is a 0. 0 minus 1 is a 1 with a borrow. 1 minus 1 is a 0. No, that cannot be right. That doesn't look right to me. This is a 1. 1 minus 0 is a 1. And then here we have 0 minus 1 being a 1 with a borrow. 1 minus 1 is once again a 0. 0 minus 0 is a 0. 0 minus 1 is a 1 with a borrow. 0 minus 0 is a 0. 0 minus 1 is a 1 with a borrow. 0 minus 1 is a 1 with a borrow. 1 minus 1 is a 0. 0 minus 0 is a 0. 0 minus 1 is a 1 with an extra borrow. But we only have to focus on this part here. Okay. Now, how do I double check that is actually correct? Well, we're plugging in and see if it works. Okay. So now we plug this in. We have 0, 1, 0, 0, 1, 1, 1, 0, plus 1, 0, 1, 1, 0, 0, 1, 0. And we want to figure out, is this going to give us what we are supposed to get? All right, 0 plus 0 is a 0. 0 plus 0 is a 0. So there's no carry generated from the addition of that column. 1 plus 1 is a 0 with a carry. 0 plus 0 is a 0. 1 plus 0 is a 1. 1 plus 1 is a 0 with a carry. Same thing here. 1 plus 0 is a 1. 1 plus 1 is a 0 with a carry. 0 plus 1 is a 1. 1 plus 1, once again, is a 0 with a carry. This is going to get boring. 0 plus 1 is a 1. 1 plus 1 is a 0 with a carry. 1 plus 0 is a 1. 1 plus 1 is a 0 with a carry. 0 plus 1 is a 1. 1 plus 1 is, once again, a 0 with a carry. So everything checked out. Are there any questions about this process? So we have figured out one end of the numbers that can generate a carry. Now we have to figure out the other end. How do you think we will figure out the other end? Yep. Yes.
In your carry section, you were doing 2 rows at the same time. Like the carry section?
The borrow?
The borrow section was doing 2 rows, the above and the below.
The first 2 rows are, okay, this row here is indicating the result of the first half subtractor. And then this row is reflecting the result of the second half subtractor. So when you combine 2 half subtractors, you have 1 full subtractor. It works pretty much the same way as carrying for addition, except the rule is slightly different in this case.
Okay, so if I did that the long way, I would need another row.
Do it the long way?
Like, for example, 0 minus 1 is 1 with a carry. And then
With a borrow.
Minus 0, borrow. 0 minus 0 is 0 with a borrow? I don't see that. Like the 5th column from the right.
5th column from the right. You mean this column?
Right.
Okay, 0 minus 0 is a 0. This one comes from the previous column.
But
so
the one
0.
after?
What?
But the one after, the one to the left of that one?
This one?
Yeah.
This is because 0 minus 1 is a borrow. As a borrow. 0 minus 1 is a 1 with a borrow.
Okay. So it's going to the left of it?
Yeah. Yep. Okay. All right. Yep.
So then no number below the number we got should generate a carry flag then.
Correct. So once we identify the range that will generate the carry flag, the other part is the part that does not generate the carry flag.
The other end.
The other end. Yep. Okay. So we have to figure out. Yep.
And that was in the one above the one you had your cursor on. Shouldn't it be? Shouldn't the leftmost column be 0 minus 1 results in 1 with a borrow? So there shouldn't be a 1 in the result.
Which one again?
The one above the one you're currently on.
This one?
No, I mean like the problem above it. Yeah, here, like the left, the 8th column from the right. Yeah, this one. 0 minus 1 is 1 with a borrow, right?
Yeah.
So that one that you have highlighted right now shouldn't be there right now. Pretty sure. Should it?
Well, it's not represented. It's not represented here.
Yeah, I'm saying
It's
it should
truncated.
in the result in the first place because that column 0 minus 1 is 1. You should have added a borrow.
Oh, you mean because this one has an implicit borrow here, I mean a 0 here, and then this becomes a 1. Whoops, alignment. And this becomes a 1.
Yeah, so
and so this should become a 0.
yeah.
Yep, you're correct. Yep.
Okay, I was just making sure I understood it right.
Yep, you understood it correctly. I was just kind of lazy because that bit is not relevant to me anymore. Okay. Yep.
Is it alright if we just do a complement plus 1 instead of the whole subtraction method?
Say again?
The complement plus 1?
You can do that too. Yeah. There are several ways to do it, but this way is more clear. It's just that to me it's clear how we find out one end of numbers that can generate the carry. But it works the same way if you try to do it the other way. All right. Okay. So this number here is is going to be one side or one end of the range. Where's the other end of the range? The other end of the range is just 1, 1, 1, 1, 1, 1, 1, 1. Okay. So to answer this question, to make the carry flag equal to 1 after the instruction, %AL can be from 101 10010 to 1111 1111. And to be very clear, I'm going to use this to represent base 2. So that would be the answer. Are there any questions about the process, of figuring out the answer in this case?
Instead of adding this to subtracted, instead of adding this to subtracted, using subtraction.
I'm using subtraction to find the answer. Yes, or that is one way to do it. There are multiple ways to do it. And this also automatically answers the other question. How do we make the result, how do we make the Z flag turn on? It answer that question also. Yep.
Can we use base 10?
Can we use?
Base 10. Base 10.
Can we use what?
Base 10.
Base 10? Yes, you can. But you have to make it clear which base you are talking about because base 10 can also be interpreted as base 16 because it uses the same first 10 digits plus A, B, C, D, E, F. Yep. All right. Any other questions about this type of question? No questions? Okay. Let's move on to some other ones, and if we have time, we can come back and look at the other flags. Yep.
So to clarify, the 10110010, the number we got, but also is the only number that'll spawn the Z flag?
Correct. Because that's how we got here is we subtracted this number. Excuse me, take it back. We subtract this number from this number. So as a result, the addition of these two, this is actually a test right there.
Gives us the 0.
Okay.
Those are all zeros. So that will also mean that Z flag is a 1 when we add that number to the original number, when we add it to 78 in base 10. Yep. All right. So let's move on to the next type of question. The next type of question is how is negative 32 represented as an 8-bit number using 2's complement? Specify the bit pattern as a base 2 number. The binary representation of 32 is 00100100000 in binary. Yep.
You could put more flair.
Say again?
You can put more flags.
Yep, but I'm letting you guys, do it unless we have time. We can come back to this one later on. Okay. The overflow, the sign flag is easy. The sign flag is basically the same thing, except you're subtracting 1 followed by 7 zeros. You're subtracting that number from 1 followed by 7 zeros, and that will give you the answer to that one. The overflow flag is the tricky one. The zero flag I answered already, so that one is okay. But the overflow is the tricky one, so we'll take a look at the overflow flag one when we have time in today's. Okay, so how is negative 32 represented as an 8-bit number? Okay, we use 2's complement. So 2's complement works like this. Okay, I'm pretty sure most of you still remember what is 2's complement. It is 1's complement plus 1, or at least that's one way to do it. So what we need to do is to apply 2's complement to 0, 0, 1, 0, and then followed by 4 zeros here. This becomes the 1's complement of the same bit pattern plus 1. 1's complement is easy to do because it's just flipping the zeros into 1's and the 1's into zeros. So this becomes 1, 1, 0, 1, 1, 1, 1, 1, and then plus 1, and all of these are in base 2 already. And once you do the addition, you end up with 1, 1, 1, and then followed by all zeros here, and that becomes the representation of negative 32. Are there any questions about this one? Just how to apply 2's complement. No questions? Okay. If I ask you to do base conversion of 66 into base 2, would that be an easy one? Most people can do it using a basic calculator or without a calculator. 66 is 64 plus 2. So anything that involves a small number of powers of 2, that is a sum of a small number of powers of 2, those are the easy ones to convert into base 2 because you just have to identify where the ones are and then you are done. All right, so second question type is done here. Third question type, convert complex addressing mode to use basic instructions, such as based addressing mode. Okay, so with this type of question, what I would make it very clear is you can only use certain types of addressing modes in order to implement a more complex addressing mode. So in this case, let's say that you can have register operands, you can have immediate operands, and then you can have indirect operands. Those are the only 3 operands that you can use. How do we do how do we implement a based addressing mode using only those 2 other types of operands? That's the question. Okay. Okay, so let me give you a list of instructions or operands that you can use. Okay, so we can use a register operand. Register operand looks like this. Okay, that's a typical register operand. We can use immediate. We know what that looks like. We can also use indirect, which looks like this. Okay, so these are the only 3 basic building blocks that you can use. Using these 3 basic building blocks, how do we implement the other more complex addressing modes? That's the question. Okay. So in this case, I want to implement something to the effect of this. Okay. So how do we do this using only the more basic ones? Now you do have to use multiple instructions, so don't even dream of doing this in one single instruction. You do need multiple instructions. The question is what type of instructions do we need in order to do this? Typically, I would also say that you can destroy one other register in the process. So you can use one register as a scratch pad, and I don't really care. Okay, let's just say ECX. Okay, you can use ECX for whatever you need to use it for in the sequence of instructions. So the question is, how do we do it? Well, the first thing you have to do is to find out what is the effective address of this guy here. This is easy. This is just a register operand, and it is already allowed, so we don't have to deal with that one. That one is easy. The other one is not something that is easy to do because it is a based operand. The effective address is L1, whatever L1 is, plus the value of EDX at that time. Is that okay? I'm hoping that most of you still remember what a base operand is. So the question is, how do we do all this? Let me see. Adding. Did I mention adding? I did. So, do we have any instruction that can do adding? Add L. Okay, all right. So the answer to this question is we have to compute using ECX to compute the effective address. So the first thing we do is we can move EBX into ECX, and then we add L, $L1 to ECX, and then we move long EAX to indirect ECX. These three instructions combined will perform exactly the same thing as that one single instruction, with the side effect of I'm using up ECX for that purpose. Are there any questions about the answer to this one? Now, since I give you base addressing mode right now, that means in the exam it's going to be something more insidious. But more, how much insidious can I get? Not a whole lot. Okay, I can only get as insidious as Intel. Wait, that is not a good statement to make. That means I can make it very, very difficult. No, that's not the case. What is the most complicated addressing mode I can ever give you in this class?
Base scale index.
D, B, I, S. The effective address of this thing is D plus B plus I times S. We haven't really talked about how to do multiplication, but you can do multiplication using addition. I'm not going to tell you guys how to do multiplication by addition, because that would not be a nice thing to do in this class. There are tricky ways to do it to make it really fast, because we know that the scale can only be 1, 2, 4, or 8. They're all powers of 2. Okay, there's a slow way to do it, there's a fast way to do it, but as far as the exam is concerned, it just has to be correct. Okay, I'm not gonna talk about it. I'll let you guys figure this one out. This is as complex as it can get. Yep.
I noticed in the notes you gave us how to do multiplication.
Right.
I noticed in the notes you gave us how to do multiplication. Right. If on the test we did that, that'd be okay too?
That would be okay if you do it correctly. Yep. But you don't really need to do it. It's not going to be much faster than doing it this way. All right. Moving on. Fix a program with different sorts of problems. Okay, we'll take a look at this one. I have an example, down the list somewhere. Make up for complex conditional branch instructions using more elemental ones, like using JO and JS to implement JL, or implement JA only using JNC, J in bracket NC, which means the N is optional. You can use JC, JNC, JZ, JNC, and JMP. So using those more elemental versions of jumps, implement the more complex ones. Okay, I'm gonna do one. You will have to kind of figure out the other ones. I'm gonna do this one. Okay, so this means I want to implement something to the effect of JL to a certain label, but I can only use JO and JS with nothing else. I cannot use JNO, I cannot use JNS, just JO and JS. So the question is, can I do it this way? Yes. Okay, and if so, how do I approach this problem? Okay, so I'm going to say here, implement JL using only JS and JO. Okay, so let's say the original instruction is JL to some label L1. I don't even care where L1 is. I just know that there's a label somewhere in the program called L1. Okay, all right. So what I'll do is I can choose randomly which one to use, because it doesn't really matter which one to use first. I can use JO, and I'll say JO to my own local label here. I'm just going to call it 10.1 as a label. So 10.1 is over here. Now, when I work on this code here, what I'll do is I'll label what it means to continue execution after JO. What if the branch did not happen? And what does it mean if I continue execution at 10.1? So over here, I'm going to write comment and say, well, at this point, I know that the overflow flag is a 0. It is cleared. Okay, this is not something that you have to do, but I find commenting, with branches like these to be very, very useful. Okay, because I cannot mentally track all the labels and the meaning of the labels. So with this one, I can comment and say, if I get to this point, it means the overflow flag is a 1. Is everything still okay at this point? Okay. All right. If I use a JL, can someone remind me what the quote-unquote L flag is equivalent to? The L flag is the same thing as the overflow flag, exclusive or the sign flag. Is that okay? Which also means, when the overflow flag is a 1, the sign flag is a 0, the L flag is a 1. When the overflow flag is a 0, the sign flag is a 1, the L flag is also a 1, and it's a 0 if they are the same. Okay? I'm hoping that most of you still remember this truth table or the meaning of exclusive OR. Is that okay? All right. So JL basically means I want to branch to L1 if and only if O and S are different. Okay, I don't care which one is a 1, which one is a 0, as long as they're different, I'm going to branch to L1. Okay, getting back to the example here. Okay, at this point I know the overflow flag is a 0, so that means if the sign flag is a 1, I can just go straight to L1. Is that making any sense? Okay, what if it's not? What if the conditional branch did not happen? If the conditional branch did not happen, that means overflow flag is a 0 and the sign flag is a 0 as well. So I should just go ahead and continue execution at this point, and I'll make a continuation point here called temp2. So at this point I have to jump unconditionally to temp2. But tag, you said that you can only use JS and JO. That's okay. Actually, there's no way around this one. There's no easy way around this one, so I'm gonna change the question itself. Yeah. So I have to be able to use unconditional branch. Okay, so I have to use a conditional branch around the whole thing. Yep.
You can do it. Your labels for temp 1 and for temp 2, your conditional branches can't be below the code that you have. Just put them somewhere else. So that, and you can use unconditional jumps inside there to move to somewhere else. I know it's kind of confusing, but that's the other way you can do it.
Yeah, but allowing unconditional branches, okay. Either that, or I can allow the JNO and the JNS. That will make it easy too, because I can have a JNS right after JS. That means it will catch all the other cases. But unconditional branch will work as well. All right, so that's good. What about this one here? The overflow flag is a 1 already. I can use JS and JO or unconditional branch. So at this point, I'm going to say if the sign flag is also a 1, that means I have to go to the continuation point because there's no way I'm going to L1 at this point. Is that making any sense? Because the moment I get to temp 1 means overflow is a 1 already. The sign flag being a 1 means that the L flag is going to be a 0, which means I should just go ahead and continue execution and not go to label L1. So that also means that if I do not take this conditional branch, then I can go to L1 over here. And that's the sequence of code. Okay, so if you look at this highlighted piece of code, that can replace a JL L1. Yep.
Well, L1 is just right after temp 1. You don't need a jump, right?
If L1 is?
If L1 is just right there between.
That is correct. But in general, L1 can be before, can be after, can be like, wherever it can be. So we cannot make that generalization. So whatever code you give me has to work in general, cannot work only if L1 is right after. All right, so are there any questions about this one? Any? Yep, go ahead. Say again? L1 is just some label somewhere. I'm just going to write a sequence of code that can be placed at one single instruction.
What is the label you want to go to?
It's somewhere.
Basically, if JL Oh, okay, so JLL1 is replaced by the whole code.
Wherever L1 is, okay, I'm just trying to write some code to replace JL1 using only JO, JS, and JMP. Are there any questions about the process of going through this? I mean, it's just reasoning through the process. No other questions? Okay. Moving on to the next one. Implement a short C++ program in assembly and not necessarily programs that we have encountered in class or homework assignments. Yep.
And also that one is JA using JNC and JMC.
No. It's a suggestion. Okay, you should think about it. I can think of a gazillion type of questions. I'm not going to give you the answers to all gazillion. I'm going to give you the answer to one. Now, how do I test this? Okay, I cannot give you a problem where you can come up with a solution, but there's no way to check whether your solution works or not. Right? So how do you check to see whether your sequence of basic instructions can replace that one single instruction that you're supposed to use? How do you test it? Change.
It's a very simple instruction.
Yep. But the first thing you want to look up is what flags are actually involved in the complex version, and then you generate all the test cases. If your replacement sequence of code works for every single case, then you're good to go. Now, how do we know all the possible cases? This. So in order to test that sequence of code, what you need to do is to use generate 4 possible test cases. One possible test case will have the overflow flag being a 1, the sign flag being a 0 after compare. The second one would have 0 and 1. The third one 0, 0. The last one is 1, 1. And then if for every single case your code is going to label L1 or not going to label L1 the same way as JL, then your code has to be correct 100%. Is that making any sense? How to check it? Yep.
What you're saying is you need to generate a case that should give that outcome, the 4 outcomes or however the outcomes are.
Exactly. And that's something that we talked about already, how to generate particular test cases. Okay. Are there any questions about how to verify your answer? Let's say, if I say, give me a sequence of code that can replace JG, okay? I'm just going to give you a clue here, okay? JG, okay? So I want to go to, I want to specify JG to L1. What flags are involved in this case? We have 3 flags in this case. And Z. Okay, so we have O, S, and Z here. There's a reason why Z is here, because JG is not J and L. Why is JG not exactly just J and L? What is different between?
Greater than, it's not equal.
Exactly. Greater than does not include equal to, but not less than does include equal to. So that's why JG is not the same thing as J and L. It is close, but not exactly the same. So JG, if you want to implement JG, you have to take a look at not only O and S, because that's the L flag itself, but you also have to take a look at the Z flag. Yep.
So is it overflow? Well, I'm gonna ask you this question, see if you answer.
The equation is already given in the notes. So if you go back to the conditional branch note, there's an equation for JG instruction. Let me just double check, because sometimes I think I have written something and it's not the case. It has happened in the past, it's possible. So I'm going to double check on that one first, just to be sure. I think by this time some of you can navigate my website faster than I can. Flags, conditional branch.
You gotta remember not to hit up too many times,
Huh?
because your notes are separated into different things that aren't all included on the topics of Moodle.
Yep.
I guess.
Yep. Okay, what about the others? Nope, not that one. This one. Nope. Has to be this one. There we go. JG is jump if and only if z equals 0 and blah 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 equals to 0. So the equation is already given to you. You just have to generate the 8 possible cases here, the 8 possible combinations. Test your code versus JG on each case. If it works identically, then your code is the correct replacement to JG. Okay. Yep.
On the test, you say we can only use JO, JS, and JZ. Does that just this include J and Z, or can we use that?
If I use the n inside the square bracket, that means you can use JG, and that means you can use the negated version too. If I do not give you that option, then you cannot use it. Like what I did here. But the principle is the same, whether you can use the negated version. I can give you something like you can use JO and JNS and unconditional branch. Okay, so you have to work with whatever is given to you as building blocks. Conjunction, conjunction, and disjunction. Yep.
Symbolic logic is often.
Symbolic logic. Have you taken it? Okay, it's going to be helpful. It cannot hurt. All right. So getting back to the questions. All right, so that one is done.
Are those the only 3 that we should really worry about? J, JL, JG, and JA for the advanced flags?
Well, that's a whole bunch here.
Yeah, well, those 6, but
Yeah.
those are the 3 general.
Yeah, those are the only ones that requires combination of the flags.
And I'm drawing a blank. What was JA again?
Jump above.
Oh.
Let's make sure conjunction is and, right? And conjunction is or.
Conjunction is and, disjunction is or. All right. Any other questions about this? About this kind of question? Okay. All right. Next type of questions. Spot problems. Okay. Let's see here. Implement a short C++ program in assembly code. I'm going to give you the exact example later on. Spot problems of the assembly code that implements a C++ program. So I'm going to give you, in this case, I'll give you the C++ code as well as my incorrect version in assembly. So you will have to spot the problems and say, well, Tech, your implementation is not correct because this instruction is not supposed to be like this, that instruction is not supposed to be like that, and you'll have to fix my program. Yep.
How many problems?
How many problems?
Do you specify how many errors in that one?
I would give you the number of problems so you can at least check off the number of items. Any other questions?
Are you going to be checking if the program functions the same or if it's like actually equivalent?
For what type of question?
For the one you're highlighting right here.
I'm seeing whether you can spot the problems and fix them. In other
Problems
words,
being bugs or problems being like.
they can be. It's common things that happens. Like forgetting a percent symbol in front of a register. Opening a paren without closing it in an indirect operand. Missing a comma. Simple stuff like that. But it can also be using a J and Z instead of using JZ when the other one is the correct one. Branching to the wrong label, like if I have a conditional statement, I branch to the end instead of branching into the else case. So those are all kind of possible type of bugs that the code can explain. One thing about this type of questions is you cannot say, I give up on your messy code tag, I'm going to re-implement the entire thing using my own code. Because I know some people in this class can do that more effectively than spotting problems of other people's code. But you have to spot my problems and fix it instead. Okay? Because that's part of the process, is to fix, is to look at the code and figure out, okay, what is wrong with it. This is another one, predict the outcome of stack-based operations. I have an example, at the end here. And then we have some stuff, that will have system surfaces involved. Okay, reading, writing, and exiting programs and stuff like that. Okay, so here's one. Write the following pseudo C++ code in assembly language. Okay. Well, first of all, if instead of just blindly writing this code in assembly, what does it do?
That's a label stack. Test to make sure that it's reading something, and then you can test to make sure that it's not in
Okay.
It's the number of bytes read is in between 1 and 10.
Yep.
It has been not
It's echoing everything from the input file, from standard in to standard out, until it hits the line feed character. It stops when it reads the line feed character. It gets out of the loop. The line feed character has an ASCII code of 10 in decimal, so that's why there's a not equal to 10. So as long as I'm reading something and it's not the line feed character, echo it back into standard out. That's all it does.
Okay, 11, 12, 13, right? Maybe 11, 12, 13, anything else?
Can you what?
11, 12, 13.
Well, it says if it's not 10, if it's not 10, stay in the loop. If I read something and it's not 10, stay in the loop. So is 11 10? Is 12 10? No, you just answer your question. Yep.
Will we have to know the ASCII code table?
No, you just have to implement the program exactly like that.
I understand. But I mean, like if we're debugging, right, you won't switch it on us.
No.
You put in an ASCII code where there was a number before.
If you
Or
do
the other
need
way
to know
around.
the ASCII code, I will give it to you. All right, so let's go ahead and write this code. And let's see, where's the notepad is right here. This is my program. Oops. All right, so let's go ahead and write that code. Since we have not talked about local variables or how to store something on the stack, we just got into that. I'm going to say that, well, it's okay to use the .data section. Okay, so .data ch is just 1 byte in this case, and then you can switch back into the .text section. .global _start _start. Someone forgot this in the program, in the previous program, file IO. Somebody forgot this part, so the program would not link correctly. It certainly did not run correctly. Okay, so now we have _start. What are we going to do? Okay, if you look at the C code here, what is the first thing we have to do? Try to read a byte, right? Okay, so try to read a byte, which means we are using system surface number 3. We specify the system surface number in EAX. We are reading from standard in, which is file descriptor 0, that is specified in EVX. We are reading into CH. We specify that into ECX. And then we are also reading 1 byte. We specify that in EDX. Don't forget to actually perform the request, which is the software interrupt instruction. When it comes back, the result is in EAX. So we have to check whether EAX is 0 or non-zero. Now, I understand that read can return a negative value if there's an error, but you have to preserve the logic of the original code. So in this case, we'll just say JZ, which means if I'm reading a 0, which means there's nothing read back, I just have to exit the entire program. So I'm going to say loop exit, and then I define loop exit right here. If I do not do the JZ, it means, say again?
Compare.
Oh, yep, you're right. Compare. Thank you.
One time the instructor forgot to put a compare instruction in the program.
Yes, my look ahead cache is not functioning.
That scared me. I was like,
Okay, so we have to compare EAX to 0 first. If it is 0, we are going to exit. If it is non-zero, we continue. The continuation part means we have to compare CH to 10. So we have compare byte in this case. With the ASCII code, well, just 10 itself is fine because that's exactly how it is expressed here. So we'll compare that to CH, and if it is the same, we also exit the loop. If we do not exit the loop, that means we have read something, and that something is not the line feed character. In that case, we'll just go ahead and do a write operation, put a 4 into EAX to specify a write operation, put a 1 into EBX to specify the standard out, and that part you don't even have to remember. There's no need to remember 0 is standard in and 1 is standard out, because it is already here and also here. Okay, so that part is like, there's no need to even remember that part. CH is where we are writing from, so that goes into ECX. We are only writing 1 byte, that goes into EDX. Perform the actual request here, and after that is done, we go back to the very beginning. I'm just reusing underscore start because there's really nothing else that I need to do, after underscore start, so that would do it. Okay, and to finish this program, now this is basically just a portion of a program, but for those of you who want to finish it off, we can just go move a 1 into EAX, and then put a 0 into EBX, our usual exit code. But that's optional because the question did not ask you to finish the entire program. Are there any questions about this answer to that question? Questions? Okay. Next question. Make the following program assemble, link, and run without errors or segmentation fault. Do not remove any instructions. You may add additional lines of code. Explain each problem. Okay. Well, I have to say do not remove anything because the easiest way to fix a problem is to remove everything except for the underscore start label. Okay, so we have to, okay, so this one is easy. I gave you guys an easy one as a test. Okay, so I'll just copy and paste it over here and then work on it. Okay, first thing is the start label is different. Okay, it should be underscore. So add underscore. Okay, this one has 2 problems. The 0 has to be an immediate operand, not a direct operand. Okay, so for immediate, and then %EAX for the register. Same thing for the other one. This one, there's no problem with it. And then we also need to add a line, dot global underscore start. Okay, so the linker can see is label. Dot text is technically not required because dot text is the default segment. So if you don't specify dot text, it's still okay. Okay, so technically you don't have to specify dot text. So if you specify that, it's good. If you don't specify that, it's still okay. On the other hand, if I have switched to the dot data section already, then you need to switch it back to the dot text section for code. Yep.
That program, will it exit?
Yeah. The only thing it does is to exit.
Isn't the number backwards?
Yeah.
Shouldn't it be, one?
Right.
Yeah.
I have no idea what system surface number 0 is going to do. So we'll have to switch that. There we go. Thank you. Good. All right.
That's okay, when the test comes, I'll forget that.
Well, what I would probably do is I'm going to write some code that actually works, and then I'll just go into the file and just randomly do stuff to it. No, just random deletion and adding stuff to it. Yep.
So that code exits, or that's what it's supposed to do. But I mean, are we supposed to be able to tell that that's what that code was supposed to do? And
I'll give you the C code. In the
okay.
case like that, I'll give you the C code.
And then we'll know what it's supposed to do.
Right. The C code is the reference. Like it is supposed to do this, and then you look at the actual code, and you have to spot the problems. Okay. This one is kind of interesting. It is the reverse of a problem that we saw earlier. use a single instruction to accomplish the following sequence of instructions, with the exception of the side effects on register EAX and EBX. Okay? So let's take a look at these three instructions here. The first one is moving immediate 0 into register EAX. The second one is move immediate L2 to EBX. And the third one is to move EAX into indirect EBX. And I want to combine three instructions into one, not counting the side effects on registers EAX and EBX. Okay, so this one is just moving $0 as the first operand to L2 direct as the second operand. That's the answer. Because the direct operand L2 is using L2 as the effective address of the second operand. And that's also what the three instructions are doing. It ends up, resetting the content at label L2 to 0. That's basically what it does. Any questions about this one? We put a 0 into the location at label L2. That's the effect of the instructions. So this one is kind of like the reverse of the one earlier, where I give you the complex version. You have to convert it into the smaller, more elemental instructions. This one gives you the more elemental instructions as a sequence, and then you have to find a single instruction to replace all of those instructions. Okay, I think we have one more here. Okay, what is the content of register EAX when execution reaches label L1 in the following code? Okay. All right, so this is new, somewhat new, and with a debugger, it's easy to do, right? With a debugger, you just set up a breakpoint at L1, stop it, and then look at register EAX, and you're all done. So without GDB, how do you do something like this? Well, you have to, or a piece of paper, okay? You can do it on a piece of paper. So I'm going to tell you guys how to do it on a piece of paper. Okay, so this is the last question here. You have to remember a few things, okay? The first thing you have to remember is what is little endian, okay? Little endian means the least significant byte is the one at the lowest address. When you push something on the stack, it is still following the same rules. The most significant byte is the one at the highest address. The least significant byte is the one at the least address, at the lowest address, okay? So you have to remember that one. The other part you have to remember is when we push something, the stack pointer is decrementing. When the stack is empty, the stack pointer is at its highest point. As you push items on the stack, it is going to decrement. Third thing you have to remember, the stack pointer points to the lowest byte of the last item that you push on the stack. Okay? So those are the three key things that you have to remember and apply to answer a question like this. So let's see how we can do it, just using those particular items, concepts. Okay, first thing is, what is this push out instruction going to do on the stack, and what is the stack pointer after this instruction? Oops, I just did something. Okay, I just scrolled it down, that's all. Okay, there we go. Okay, the first thing we want to do is to say, okay, when these bytes are stored, we know that we are storing 4 bytes because it's a push long instruction. So the question is, in terms of byte ordering in memory, which one is going to be the highest, which one is going to be the lowest on the stack? It is still using little endian, so that part has not changed since the beginning of this class. So in this case, which byte is the highest byte? AB is the highest byte, okay? That is the most significant byte. So in terms of byte ordering, we have AB being the most significant byte at the highest address, and then we have CD being the next one, and then we have 1, 2, and then 3, 4 is the least significant byte. It is at the lowest address after the push long instruction. Are we doing okay with that concept? Now, where ESP is pointing exactly, I don't really care. The only thing I know is after the push long instruction, ESP is pointing here, because it points to the lowest the lowest byte of the last thing that we pushed. And that byte with 34 in hexadecimal is the least significant byte or at the lowest address. Okay. What about the second instruction? The second instruction is a little bit tricky, but not too tricky. It's not something that you have not seen before. It has a leading zeros. It has two leading zeros. Sorry?
0076?
It has 0076, so we have 00 here being the more significant byte, and then 76 being the least significant byte. And obviously after that, the stack pointer will be pointed to 76. The third instruction looks a little bit nasty because it is just copying 2, 3 into wherever ESP is pointing to. But we know what ESP is pointing to. It's pointing to the byte that is currently saying 76. So we will change that to 2, 3 in hexadecimal. Like so. And the last instruction is to pop L into EAX, which means we are taking the 4 bytes starting with the byte that the ESP is pointing to, and then 3 other bytes on top of that into EAX. So once again, we are moving or copying multiple bytes into a 32-bit register. Which concept do you think is going to be important here? We have 4 different bytes going into a single register. Little endian, okay? Which byte is the least significant byte? Which byte is the most significant byte? What do you think? Okay, 1, 2 is the most significant byte, so EAX ends up with the value of 0x12340023. And obviously after that, the stack pointer is going to be moved as well. Okay, so after that, the stack pointer will be moved to here. Yep.
Where is little endian here? Why it's not stacked like vice versa? I mean, 34 first, 1 plus, see here.
Little endian is important because we are copying multiple bytes from memory into a 32-bit register.
But why we start from?
Because we are still playing by the same rules. The byte at the highest address becomes the most significant byte. The byte at the lowest address becomes the least significant byte. So in this case, 1, 2 is the most significant byte in EAX because in memory it was the one that is at the highest address.
So in memory, it's stored like 34 on the left.
Say again?
In the memory, it's stored like 34 on the left.
In memory, it's only high location and low location. So in this case, if I write these bytes from left to right, AB is going to be the leftmost one, and then 2, 3 is the rightmost one. If I dump these 6 bytes on a single line.
AB left, but is little endian should be vice versa.
No, we did a reversing already when we wrote the bytes on the stack. I think it's best to use GDD to illustrate, just in case I make a mistake. Because I have been corrected several times already today. So let's go ahead and double check. Yep.
So if you did like a pop AX instead, it would the pointer would be a 3-4, right?
That is correct.
Okay.
And then AX would end up with 0023. Right. Yep. Okay, let's double check and make sure, so we can, be 100% sure about the correctness of this answer. Okay, that works. Okay, and the instructions are over here. A, B, C, D, 1, 2, 3, 4. Okay, so yep, go ahead.
Just a quick question. If you do a pop L on an AX, it'll give you an error. It won't compile.
If I do a pop L
On a pop L AX.
AX, it will give you an assembler error because the length, the width of operation you specify with the opcode is not consistent with the operand.
So you can never do like pop AL or pop AH because you can only pop W and only pop L? Or can
Yes.
you do pop B now? There's no such thing as pop
There's
B.
no pop B. The instruction does not exist.
Okay.
Okay, so we'll take a look at the program, put a breakpoint on line 3, so we'll start from scratch here. Okay. I'm running the program. We are now encountering the first instruction. Take a look at ESP at this point. Okay, make a note of that. Single step through the push out instruction. Look at ESP again, and then take a look at the memory content at that location. So x/4b, dumping 4 bytes in hexadecimal, and we want to start with the location that the stack point is pointing at. We should see 3412 CD AB because when we list bytes from memory content using the X command, the leftmost part is the least significant byte or the lowest address, and then the rightmost part is the one at the highest address. So we should see, in this case, 3412 CD AB. That's exactly what we're seeing. Okay. We single step through the second instruction. Oh, yeah, we just single step through the second instruction, and I want to repeat the dump command, but this time I want to display 6 items instead of 4. And at this point, we should see 3412 CDAB. Those are the same thing as last time. And then we have 2 additional bytes, which are. No, I take it back. I take it back. It should be. The first byte is a 76, and then 00, and then we have 3412 CDAB. Okay, because the stack pointer points to the lowest byte that we just pushed. Okay, in this case, the lowest byte is the 76 byte of the word that we just pushed. Okay, and that's exactly what we are seeing. Let's move this over. Is that okay? Okay, so the third instruction is to overwrite the least significant byte, or the byte that is currently 76 with 23. So we want to do the memory dump again and make sure that that is the case. So at this point, this is the byte at the lowest address. This is the byte at the highest address as far as the pop L command is concerned. So the result in EAX should read as 12340023. Okay. So let's single step through the pop L instruction and then take a look at EAX, and it is 12340023. Are there any questions about this particular answer, or the answer to this question? Okay. Well, we have just seen all the different types of questions that will be in your exam. The push pop thing, I can push and pop a few times, but it doesn't really change the nature of the question. Okay. The push instruction is just putting more items on the stack. The pop instruction is just removing things from the stack. Are there any questions about this stuff?
Implementing a short C program.
Yeah, we just did.
Oh.
With the
mean
program
the
that
stack
echoes
one?
everything up to the line key character.
The
That's
stack,
what it
the one with the stack?
Sorry?
The one with the stack?
That's what we just did. Yep.
So for example, we won't be dealing with an example.
Say again?
For example, we're not dealing with an example.
No, the exam does not include anything on subroutines. So we have push and pop, but not subroutines. Sorry? Which one? Which one? I think I said, if I have enough time, I will go back to this one.
Overflow, yeah.
The overflow flag? Okay. So let's take a look at this one, and we want to find out, when the overflow flag is going to be set and when the overflow flag is going to be cleared. Now, the overflow flags, there are several ways to look at it. you can look at the definition of the overflow flag being, looking at the sign flags of the results and also the starting operands. But you can also look at the overflow flag as the sign of the result does not make any sense. Okay, and that turns out to be, I think, is the easier way to look at this one. So let's take a look at using that interpretation of the overflow flag to figure out the range of numbers that can make it turn on, and the range of numbers that can make it turn off. So let's take a look. Okay. So we are now revisiting that particular question. Okay. 78 plus what will trigger overflow flag to be a 1? That's the question. Okay. So we want to add something to 78 so that the sign of the result does not make any sense. Okay. If I add a negative number to a positive number, the result can be positive, can also be negative, right? So I don't want to do that because there's no such thing as does not make sense. If I add a positive number to a positive number, the result should be positive. Oh, okay. So that means if the sign flag is on after the addition, the overflow flag should be on. Is that okay? Yes. In the case of an 8-bit number, what is the sign flag? You have 8 bits, bit 0 to bit 7. Which bit is the sign flag? Bit 7 is the sign flag. So if the sign flag is on but everything else is off, what is the value? Negative. Well, when you look at it from an unsigned perspective, it's 1 followed by 7 zeros, right? Okay, so that's 128. So that means to figure out the smallest number to trigger the overflow flag to be on, it's 128 minus 78, and that turns out to be, don't tell me, I can work this one out. I think it's 50. Okay, sorry? I got a calculator up here, yes. Okay, so 50 is the smallest number you can add to 78 and trigger the overflow flag to turn on. What is the largest number you can add to 78 and still trigger the overflow flag to turn on? Okay, I'll give you a few choices. 127, 128, 255, or 256. 127 it is.
128, 255, and 256 don't exist in sign interpretation of 8 numbers.
Yep, exactly. So 78 plus 50 turns out to be negative 128. Overflow flag is 1. 78 plus 127 turns out to be some negative value. The overflow flag is also going to be turned on. Well, it's some negative value. I don't really care the exact value. As long as it's negative, the overflow flag is going to be turned on.
So basically for 127 it's about the size, about the size flag, and the next one is coming like the negative number as well.
If you add a positive number to a positive number, the result should be positive.
And this is for a negative number.
If it becomes negative, in a sign interpretation, then the sign does not make sense, and the overflow flag is 1. Okay, well, I just answered that question. I thought it would be longer, but it turned out that way. Say again?
Oh, ye little faith.
All right. So are there any other questions about the type of questions that you might see? Any questions? It's open book, open notes. Okay, if someone can figure out all the possible permutations of these questions, you can bring the answer to all the possible permutations.
You can give me like an additional week and see if I can develop some way to read your mind.
Then you might have some unexpected consequences that will land you in jail. It will go viral. But are there any questions about these things? Because if there are no questions about these, the exam is next Tuesday, so we have 1 week from today to basically for you guys to study. we do have a homework assignment due on Thursday. As much as I promised, not promised, I told a few people that I would try to stay quiet and not mention that. I do want to mention that, so that you guys will work on it. Yep.
You expressly forbid me from mentioning. You didn't tell me you weren't going to. You told me not.
Not to mention there's a homework due on Thursday. I was actually surprised. I was pleasantly surprised that quite a few people turned it in over the break. Some people turned it in before the break. So it's wow. I'm impressed. Yep.
So I got the homework to work kind of without a call return. Do you still want us to implement that if I can do it without it?
Without calling and returning?
Yeah. The only thing is I had an extra null pointer at the beginning of my string, which didn't make any sense.
It does.
To me, it didn't make any sense.
You get an extra no at the beginning of the output file because you are considering there's an extra input right after you ran nothing from the read operation. So you have to check so you have to check your conditional statement and make sure that when you realize that you did not read anything, don't echo anything to the output. But since you're not using recursion or using call and return, I'm not quite sure how you do it.
I was able to do it without call and return, but then I just got the extra null pointer. That's all.
Okay. All right. Any other questions? Now on Thursday, what we'll do on Thursday is I'll give you the answer to the flip homework, because it's like a few lines. It's a really neat one. And then we'll start to move on to passing parameters on the stack and also having local variables on the stack. So finally we are starting to get into that stuff. Yeah. Is that the time? Okay. Well, we can do that.
I think you started sideways.
For the homework, this one to find back. I'm not sure. I can't figure out what I did wrong other than if I did anything wrong other than mixing up JL and JB.
Yeah. What I can do is I can send you my test cases, so that way you can know exactly what test cases I used for that skill. Send me an email and I can confirm.
How much points did you take off if it was just that mistake?
I give you 5 test cases, and then those 5 test cases, account for all the points. So if you miss one, it'd be 1/5 of the points. If you miss 2, it'll be 2/5 of the points.
Okay. I think I missed 3 test cases, but the only reason I missed them was because
so because you flipped the side, because you used the incorrect conditional branches.
We can play it.
Okay.
So I can do everything in the lab. I'm actually in the lab. So
You have a question?
In my output file,